Good morning, everyone. Today I'm actually talking on multivalued dependencies and fourth normal form. Why multivalued dependencies and fourth normal form I'm discussing here? Because fourth normal form is actually based on the multivalued dependency. In order to avoid multivalued dependencies, the fourth normal form came into picture. So now, before going into the definition of fourth normal form, we will just see what is the definition of multivalued dependency. Let's take an example. So in the example emp relation, we have an emp relation with two MVDs. That is E name multi-determines P name. I have a two FDs. E name multi-determines D name. We will come across such table. When we come across such table like employee table, what actually you're seeing in employee table? E name multi-determines P name means what? E name, an employee name or each and every employee can work in more than one projects. So E name actually the employee name with the functional dependency P name, I have multi-values, right? One employee can actually connect to the any number of projects or can work on any number of projects. So that means Smith to P name, it is actually multi-values are generated. That is why we call it as a E name multi-determines the symbol is like this. P name. So that is one employee can work in many. I have one to many. So that means I have a multi-value. In the same way, if I take an example, E name multi-determines D name. So that means one employee can actually have more than one dependent. This D is not department name, it is a dependent name. Can have more than one dependence. Both are true, right? So that means my ename attribute is actually multi-determines P name as well as it multi-determines D name. But this P name and D name both are independent. They both are actually not connected to each other. This two disconnected attributes or two independent attributes. Two independent attributes. Two independent attributes is actually two independent attributes which are actually multi-determined by a single attribute ED. Now you understand? So these two FDs are in a single table. So when such two FDs which is multi-determines the other attribute is there in a single table, then how the values will be there? Let's check here. Smith actually is working in two projects X and Y. But Smith is actually have two dependents, that is John and Anna. To make this database, that is an employee database, consistent, in order to avoid generating a spurious tuples, if these two multi-determines functional dependency is combined in one table, what kind of data will be generated? The combination of between these two has been generated. So that means Smith X once combines with John and X project once combines with Anna. In the same way, Y project combines with John and Y project combines with Anna in order to maintain the what I can say, consistent data. So this is generated like this. See here, Smith is having two projects. Each project is actually have two names. That is John and Anna. So when I do like this, why I'm avoiding a spurious tuples here? When you break this and then join back, you should get the same set of attributes. There should not be a loss or additive. So like that's why we will make a combination between these two here. Is that clear? So now, so by having such data, you can see the redundancy is more here, right? The redundancy is more. So what kind of dependency we call it this as? It is called a multi-valued dependency. So that means in a same table, I have more than one multi-valued attribute, right? Where each of those multi-valued attribute, which is multi-determined by the same attribute. So that's why we call it as a multi-valued dependency. Now let's check what is a definition of multi-valued dependency. Now let's go back to this. The multi-valued dependency and fourth normal form, right? The definition of multi-valued dependency. Multi-valued dependency, X multi-determines Y specified on relation schema R, where X and Y are both subsets of R, obviously, right? Specifies the following constraint on a relation schema for the current state R of R. If two tuples, this constraints again for the current state, I'll just have to check the constraint, the upcoming constraints on the current state of R. In the current state of R, if I'm able to find this constraints, what I'm just checking now, then obviously it is a multi-valued dependency. If two tuples, T1 and T2 exist in R such that T1 of X is equals to T2 of X, then two tuples T3 and T4 should also exist in R with the following properties. Let's see what is that following properties. Let us consider this example. Fine. Let me start. What is my current state of R? This is my current state of R in a relation schema R. What is my current state? These four tuples I have. That's my current state. First, let me apply a condition. What is that condition? This is my condition. If two tuples T1 and T2, let me consider the first tuple as T1, second tuple as T2. If two tuples T1 and T2 exist in R such that T1 of X is equal to T2 of X, andre no, this is my X, Y, Z. T1 of X, Smith, is equal to T2 of X, Smith only, correct? No? If two tuples T1 of X is equals to T2 of X, then two tuples T3 and T4 should also be existing. So then there should also be T3 and T4. So let me change the color for T3 and T4. T3 and T4. The two other tuples, the T3 and T4, is also existing. Should also exist in R with the following properties where we use Z to denote what is my Z? R minus what is my relation? X, Y, Z, E name, P name, and D name. What will be, this is equals to Z. What will be Z? R minus X union Y. What is X union Y? E name and P name is my X union Y. If I minus this from the R, whatever the remaining attribute I have, that is my Z. Correct? No, D name is remaining. That should be my Z. Remaining a complete attribute should be the Z. So that is my Z. Then the condition. If T3 of x is equals to, so that means I'm just checking all these is equals to each other. See, T3 of x is Smith is equal to T4 of x. Who is this? Smith only, right? Smith is equals to T4x is Smith. T1 of x andreno Smith. T2 of x andreno Smith. You can also write it directly. You write T1 of x is equal to T2 of x is equal to T3 of x is equal to T4 of x. You can also write like this, however you want. But the next one you can't write like that, okay? So, yes, these now all these four tuples are equal with each other, right? Then what will be my next condition? My next condition is then if these four attributes of x is equals, then T3 of y should be equals to T1 of y. Where is T3? T3 of y should be equals to T1 of y, and T4 of y is equals to T2 of y. It is equals. This is x is equals to x, and this is y equals to y. Correct? This is also true. This is also true. Then T3 of z, next comes to the z part. X I have done, y I have done, and we have to go for a z. T3 of z is equals to T2 of z. Where is T3? T3 of z is what? Anna is equals to T2 of z is Anna, and T4 of z is John, T1 of z is John. If this is equals, then if all these three conditions is true, then we call it as it is a multivalued dependency. By using these three, you can actually check that every attribute of multi-determined attribute, P name and D name is combinationally they have generated, right? Combination generated. So that combination I'm checking here. So there is a one rule that there is no rule that the T1 order should go like this. No, for a given table, the order can change. You can say T4, you can make any of the order, T2, T1 also you can make, or T4, T2, T3, T1 also you can make it. But you can, if you feel it is actually a multi-valued attribute, if you have, then these combination you can make however you want and then prove for this condition. Is it clear? So this is multivalued dependency. Now, a multivalued dependency, if for any attribute multivalued dependency, if you say trivial, right? It is a good multivalued dependency. Okay, multivalued functional dependency, which is good actually, if you say, which you can accept is when your y is a subset of x. Y should be a subset of x, or x and y union should be equal to r. X and y union should be equals to r. If any of these two satisfies, then I don't have to worry with those multivalued dependency. Is it clear? When these two is not happening, then there is a problem. Then what I should do? I should decompose it. Whenever x multi-determines y holds, we say x multi-determines y, because the symmetry in the definition, whenever x multi-determines y holds, so does x multi-determines z. Hence, x multi-determines y implies x multi-determines z, and therefore sometimes I can write like this. X multi-determines y and z. X actually multi-determines both the attribute that y and z. I can actually write in this way. Fine. You just check. Now, what is my this dependency here? E name multi-determines P name. First check is first condition here. I'm talking about this condition. If y is a subset of x, This is Y. Is this subset of X? No. You know what is subset? It is not. Okay, at least can you say this X union Y is equals to R? What is X union Y? E name comma P name is completely R? No, there is one more D name. So this is not a trivial, good functional dependency. Okay. Multivalued dependencies and fourth normal form. Now we will see a fourth normal form definition. The fourth normal form definition is a relation. What do you see? Okay, I have forgotten one more point. Uh, so when you check here, in this table, this is an example table. Always in multivalued dependency table, there is one hint for you. That is all the attributes are the key. That is the first one. All the attributes are the key. In such case only you could able to see the multivalued dependencies and having a two multivalued attributes, more than one. Second one, when all the attributes are key, then always this will be in BCNF. Always that table will be in BCNF because I can't generate any FTs here because all the attributes are key here. So that means all the attributes are key. I don't have any FDs. So that means it is in BCNF. It's in the highest normal form. I can go to 4NF only when the table is in BCNF. Right? Okay, let's check here. Now definition of multivalued. So definition of fourth normal form. A relation R is in 4NF if and only if the following conditions are satisfied. What is the following conditions? It should be in the BCNF. Obviously, the table should not have multivalued dependency because even after BCNF, there was some tables where we could see redundancy and this multivalued dependency was actually arrived. So hence, which was not solved by BCNF, and hence we generated a fourth normal. But this kind of relation is very, very, very rare in the real scenario. But I can always say it's absolutely nil and I can't say it. It is 1% maybe generated such relations. For that, they came up with a fourth normal form, which should avoid generating the multivalued dependencies. Okay. So we can state the following points. An all key relation is always in BCNF. An all key relation is always in BCNF. Correct? So a table will be all key relation. If it is in all key, then it will be in BCNF because there will be no FDs because everything is a primary key. And all key relations such as an EMP relation in the above figure, which has no FDs but has the FD is not there, but they have multi-value dependencies, that is E name, multi-determines P name and D name, which is not in 4NF. A relation that is not in 4NF, what you will do due to non-trivial FT. What is non-trivial FT? To make it, how do you check whether it is trivial or non-trivial FT? We check the previous condition that either Y should be a subset of X, or X union Y is equals to R. It should be. So it is not there for me in both the cases. So that means it is non-trivial multivalued dependency. So if that is a non-trivial multivalued dependency, then it must be decomposed to convert into a set of relation. It should be divided, broken down. The decomposition removes the redundancy caused by MBD. So now let's check the decomposition here. So let's check the same example. The example is EMP. The example is the same table. How do you decompose? decompose between the two MVD. What is your MVD? Ename tends to pname and ename tends to dname. So I'll create the two tables, EMP projects and EMP determinants. So my FDs. Now you just check this table, EMP projects. What is that I have? Check whether this is a trivial MVD. If it is a trivial multi-value dependency, then you don't, we assume that it is in A4 and F. There is no harm keeping trivial MVD. So now just check it. What is the rule? Y should be a subset of E name. It is not there. Or X union Y is equal to R. Yes, E name comma P name is actually a relation. X union Y is equals to R. That is M project. In M project, I have only two. That is X and union and Y. In the same way, I can check for the P name. Now, these two is, I call it as a trivial multi-valued dependency. Thank you. So now the figure B and B, M projects and M dependents are in a 4NF, fourth normal form.